Hello, you're welcome back. Remember to subscribe, like, and share so that everyone can follow this educative channel. All right, let's dig right in. So, in this video, we are going to look at the overview of action potential. Now, when we talk about action potential, we are basically talking about the electricity that flows through neurons. Now, previously, we've looked at excitable tissues, and these excitable tissues are tissues that are capable of generating electrical signals each time they are stimulated. So a neuron is an example of an excitable tissue. A muscle cell is an example of an excitable tissue. They are excitable in the sense that they have the ability to generate, propagate, or respond to an action potential each time they are stimulated. Now let's look at action potential. There are phases of action potential. The first one is a resting state. And in a resting state, a neuron or an excitable tissue is in a resting state. It means that there is no stimulus flowing through. It has not been stimulated, and for that matter, there is no engagement within the cell. No ions are actively moving in one direction. Even if there is that net movement of ions into and out of the cell. So we call it the resting state. And the resting state, for instance, of a neuron measures a voltage of about minus 70 millivolts. So at a resting state, if you measure the voltage of a neuron, the neuron will have a voltage of about minus 70 millivolts. Now, as soon as you begin to stimulate this neuron, it moves from a resting state into a depolarized state. This is when certain channels like voltage-gated sodium-ion channels are opened, and then you enter into a depolarization stage. The next stage is repolarization stage, where voltage-gated potassium channels are open, and the last stage is hyperpolarization. So let's visually inspect each of these stages and see. Now, this is a typical cell, for instance, a neural cell, having these channels, voltage-gated sodium-ion channel and a voltage-gated potassium ion channels. These channels are going to be used when we are talking about action potential. Now, take note that as far as distribution of ions are concerned, you have more sodium ions outside of the cell, that is the extracellular fluid, as compared to that of intracellular fluid. The same vein that you have more potassium ions inside the cell as compared to outside of the cell. So as soon as this cell, for instance, a neural cell is stimulated, certain channels are going to open. But take note that at rest, the resting membrane potential of the cell is minus 70 millivolts, as I have aforementioned. And at that state, you find out that both sodium ion channels and potassium ion channels are closed, as you are seeing here. So this channel is closed, that is sodium ion channel is closed, potassium ion channel is also closed. But as soon as you begin to stimulate this neuron, then in the first place, sodium ion channels will open. Remember that the voltage is already minus 70 millivolts. But as soon as you stimulate the cell, voltage-gated sodium ion channels will open. What do you think will happen? Your guess is as good as mine. So as long as sodium ion channels are open, due to concentration gradient, sodium ions are going to influx the cell. That is, there will be movement of sodium ions from outside here to the inside of the cell. Now, because sodium ions are positively charged, as they are moving into the cell, it will drive the cell from minus 70 up to a more positive state. That is, from minus 70, it will be moving to minus 69, minus 68, minus 67, and you'll be moving up like that. So in that state, we say you are depolarizing the cell. Remember that a polarized cell is negative. And so if you are making it positive, you are depolarizing it. So the stage of depolarization basically is the state where voltage-gated sodium ion channels are open, and then now they are trying to drive the cell to a more positive state. So that is depolarization. Now, visually or graphically, this is how depolarization is occurring. I will use this as a case study. So here, the cell is at a resting membrane potential of about minus 70 millivolts. And then voltage-gated sodium channels are open. Sodium ions are coming in. So whilst they are coming in, graphically, the membrane potential will start moving up like this. So this is the graphical representation of a depolarization. So as long as voltage-gated sodium ion channels are open, there will be an accent within the membrane potential. So it will start driving the cell more positive. And as you are moving up like this, you are moving it more positive. So from this stage up until this stage, that is what we call depolarization. Now, if you look at this diagram, this is a cycle that continues to go on. So there will be depolarization as long as voltage-gated sodium ion channels are open. That is what you are observing at this state. So over here, when sodium ion channels are open, sodium ions are entering the cell as you are seeing. And we can see depolarization taking place in the next phase. So in point 2, depolarization is taking place. But in point 1, at resting membrane potential, there was no depolarization taking place. But we can see here that depolarization is taking place. And I have said that depolarization is when sodium ions are now moving in as a result of the opening of what? Voltage-gated sodium channels. Now, the next stage we want to talk about is repolarization. Now, in the next stage, which is point 3, that is when depolarization ends. So take note that over here, more sodium ions have entered the cell, and the cell has attained a voltage of about plus 35 millivolts. Then the first thing that happens at this stage is that voltage-gated sodium ion channels will close. Immediately or concurrently, voltage-gated potassium channels will open. As soon as that happens, we will see potassium ions going to leave the cell to the outside of the cell. That is when we begin to see that graphically the voltage will begin to drop. The membrane potential will begin to drop from plus 30 millivolts back down to a more negative state. So graphically we can see that if you look at this point, we can see that the membrane potential is now trying to come back down. So from plus 35, it is coming down to, let's say, 34, to 20, to 0, down to minus 55, down to minus 70 millivolts. So this is what we term as repolarization. And that is a graphical representation of repolarization. So take note of these stages. And one thing you need to recall is the nature of the channels at each stage. At resting membrane potential, all the channels are closed. During depolarization, only voltage-gated sodium channels are open and sodium ions are coming in. During repolarization, voltage-gated potassium ion channels open whilst voltage-gated sodium channels close. Okay, so this will continue to happen until more potassium ions leave the cell, driving the cell back down to a more negative state. So this is what happens. I want to use this diagram graphically to show you what happens. So as long as sodium ions are coming in and then potassium ions are coming out, we'll see this ascent and descent. And this is what we term as action potential. But it doesn't end there. You will see that the cell goes beyond. In fact, the membrane potential goes beyond minus 70 millivolts when it is dropping down. Okay, so when it goes beyond minus 70 millivolts, we say that the cell has become highly negative. In this case, it enters into a stage of hyperpolarization, which is the final stage of action potential. And that is what we are seeing here. So graphically, at hyperpolarization state, the cell goes beyond, or the membrane potential goes beyond the resting state of what? Minus 70 millivolts. That is hyperpolarization. Then another thing happens. You would see that before a cell can begin, or the next cycle of action potential can happen, there should be a refractory period. Refractory period is when the cell tries to establish or try to restore the membrane potential back to a resting state. So until a resting state is achieved, we cannot start the next cycle of action potential. So take note, before the next cycle of action potential can begin, the membrane potential needs to come back to a resting membrane potential of minus 70 millivolts. So peradventure, if during repolarization and hyperpolarization, the cell was driven to minus 90 millivolts, the voltage needs to come back to minus 70 millivolts. That is where channels or pumps like sodium-potassium pump, we need to begin to pump 3 sodium ions in and move 2 sodium ions out. By so doing, you are able to bring the cell back to its resting membrane potential so that the next cycle of action potential will continue. And this is how the wave of action potential takes place within a cell. So at green, there is an excitable membrane. Here, there is a refractory period. And then at red, there's action potential in progress. So this will continue in a wave-like portion until the action potential arrives at the axon terminal. Okay, so this diagram shows ions flowing into the cell, driving the cell to negative, causing action potential to occur. And when we say action potential, it is a cycle of depolarization, repolarization, and hyperpolarization. And now you understand the nature of the channels at each stage. In summary, during depolarization, voltage-gated sodium channels are open, voltage-gated potassium channels are closed. During repolarization, voltage-gated sodium channels are closed, voltage-gated potassium channels are open. During hyperpolarization, voltage-gated sodium channels are closed, voltage-gated potassium channels remain open, and leaky channels will even continue to pump out more potassium ions. So this brings us to the end of this video.